We're going to evaluate the integral of natural log of square root of x plus square root of x plus 1. First, you'll make the following substitution. Let y be square root of x plus 1. That makes y squared x plus 1, and x equal to y squared minus 1. And we need square root of x, so that's equal to square root of y squared minus 1. And finally, dx is equal to 2y dy. Let's express this integral in variable y. It becomes the integral of natural log of the square root of y squared minus 1 plus y times 2y dy. And we'll evaluate this integral by using integration by parts. First, we'll start with u. U is going to be natural log of square root of y squared minus 1 plus y. Let's compute du and simplify it as much as possible because it is critical to solving this problem. In the denominator, we put square root of y squared minus 1 plus y. In the numerator, we put the derivative of the denominator, which is 1/2 y squared minus 1 to the minus 1/2 times 2y plus 1 dy. So let's simplify this even more, a lot more. Du, and now looks like this. We have a y divided by square root of y squared minus 1 plus 1, which I'm going to write as square root of y squared minus 1 divided by square root of y squared minus 1. All of that divided by square root of y squared minus 1 plus y times dy. So du is equal to y plus square root of y squared minus 1 divided by square root of y squared minus 1 divided by square root of y squared minus 1 plus y times dy. Now, these two can be they are in the same denominator, and let's rewrite that. It will make our computation easier. So du is equal to y plus square root of y squared minus 1 divided by square root of y squared minus 1 times square root of y squared minus 1 plus y dy. And you can see y plus square root of y squared minus 1 divided by square root of y squared minus 1 plus y cancel, and that leaves a simple form for du. Du is equal to 1 divided by square root of y squared minus 1 times dy. Now let's go to dv. Now dv is 2y dy. Normally, 99 times out of 100, v is going to be y squared. But we are allowed to add or subtract any constant that we wish, because adding a constant will still make dv 2y dy. So I'm going to select v to be y squared minus 1, and that's because our du is 1 divided by square root of y squared minus 1. Those will be simplified much easier. So let's return to the original integral. It was the integral of natural log of square root y squared minus 1 plus y times 2y dy, and that's equal to u times v, y squared minus 1 times natural log square root of y squared minus 1 plus y, and then minus the integral of v du, and by our selection of v, that integral is y squared minus 1 divided by square root of y squared minus 1 dy, and that of course simplifies to just square root of y squared minus 1. So this is equal to y squared minus 1 times natural log of square root of y squared minus 1 plus y minus the integral of square root of y squared minus 1 dy. So all we have to do now is to evaluate this integral, and we are done. And this integral is evaluated by trigonometric substitution. So let me draw a line like this and zero in on this integral square root of y squared minus 1 dy. The way it is, the trig substitution is y equals secant of theta. dy is secant of theta times tangent of theta, d theta, and y squared minus 1 is secant squared of theta minus 1. Of course, that's equal to tangent squared of theta. Therefore, this integral now after trig substitution becomes the integral of square root of tangent squared of theta times secant of theta times tangent of theta d theta, and that's equal to the square root of tangent squared is tangent times another tangent we have, that's the integral of tangent squared of theta times secant of theta d theta. To evaluate this integral, we have to use this trig substitution and replace tangent squared of theta with secant squared of theta minus 1. So this becomes the integral of secant squared of theta minus 1 times secant of theta d theta, and this is difference of two integrals. The first one is secant cubed of theta minus the integral of secant of theta d theta. Now both of these integrals were solved in earlier videos, and these are important enough because they occur all the time, so you should know what they are. The integral of secant cubed of theta is 1/2 secant theta times tangent theta plus 1/2 times the natural log of absolute value of secant theta plus tangent theta, and the integral of secant is natural log absolute value of secant of theta plus tangent of theta. Of course, we can simplify this. Our answer is 1/2 secant theta times tangent theta minus 1/2 natural log of absolute value of secant of theta plus tangent of theta. So now what we want to do is express this in variable y. Recall that our substitution was y equal to secant of theta. If we draw a right triangle like this with this angle theta, secant is hypotenuse divided by the adjacent side. By Pythagorean theorem, that makes the opposite side square root of y squared minus 1, and that makes tangent of theta square root of y squared minus 1. So in variable y, our answer is 1/2 secant theta, which is y, tangent theta, which is square root of y squared minus 1, minus 1/2 natural log absolute value of y plus square root of y squared minus 1. Now let's return to the integral in variable y. That integral was natural log of square root of y squared minus 1 plus y times 2y dy, and that was u times v, so that's y squared minus 1 times natural log of square root of y squared minus 1 plus y minus the integral of v du. That was the integral of square root of y squared minus 1. We now solved this integral, evaluated it, so this is y squared minus 1 natural log of square root y squared minus 1 plus y, and then minus this integral in variable y, so let's put this in brackets. It's 1/2 y times square root of y squared minus 1 minus 1/2 natural log of absolute value square root of y squared minus 1 plus y. And so this is equal to y squared minus 1 times the natural log of square root of y squared minus 1 plus y minus 1/2 y times the square root of y squared minus 1 plus 1/2 natural log of absolute value square root of y squared minus 1 plus y. And now our last step is to go back to variable x. Now recall, the original integral was the integral of natural log of square root of x plus square root of x plus 1 dx. We made the substitution y equals square root of x plus 1. So y squared was x plus 1 and x was y squared minus 1, and then square root of x, of course, was equal to square root of y squared minus 1. So let's go back and substitute and rewrite the final answer in variable x. So first we have y squared minus 1. Y squared minus 1 is x times the natural log of square root of y squared minus 1, that's of course square root of x, plus y, that is square root of x plus 1, minus 1/2 y, which is square root of x plus 1, and then times square root of y squared minus 1, that's square root of x, plus 1/2 times the natural log of absolute value of square root of y squared minus 1, that's square root of x, and plus y, which is square root of x plus 1. And then we add a constant of integration here. But we can simplify this a little bit more, and the reason we can do that, right over here, there's no need for absolute value because square root of x plus square root of x plus 1 is never negative. So let's rewrite it like that. We have x times the natural log of square root of x plus square root of x plus 1. And then we can combine, since both of these are under the radical, we can write this as minus 1/2 square root of x squared plus x, and then plus 1/2 times the natural log of square root of x plus square root of x plus 1 plus c. Now further, these two terms can be factored, or we can factor natural log of square root of x plus square root of x plus 1. So let's write our final answer to this problem. It is x plus 1/2 times natural log of square root of x plus square root of x plus 1 minus 1/2 times the square root of x squared plus x plus c.